excited to share with you all a little bit about structural materials and my research. So I'll be focusing on future materials for aerospace engines, in particular ceramic composites. So thanks to the MSA for putting these talks together. And I have two funding sources, the National Science Foundation and there's a collaborative turbine materials research center with UCSB and a Japanese company called IHI. Let's start a little bit about me. I'm originally from Philadelphia, Pennsylvania, and moved across the country to Santa Barbara for grad school. I'm a first generation college student. I really had zero plans to pursue a PhD. I really didn't know what it was. My family didn't go to college. I'm first gen, so I didn't really have a support system. So hopefully I can share a little bit about how the heck I got here. Like Allison mentioned, I'm a triplet, so family is everything to me. Here's a picture of me and my sisters in Philly last December. And I originally got interested in material science in high school. I had some really amazing teachers that I still keep in touch with today that really helped foster my passion for engineering and material science. So after that, I went to Penn State from 2014 to 2018. Super big school, super big football fan. So it was a really fun college experience. I had a really great study group and really fun whiteboard walls where I could study all the material systems that I guess I'll talk a little bit about today. And hopefully this is relatable, but I'm sure all of us have spent a lot of time working hard and sacrificing sleep. So good job to all the undergrads out there that are working towards finishing their degrees. Through undergrad, because I had zero plans to pursue a PhD, I did a lot of research internships in industry. So one that was really notable and influential to me was my internship at GE's research center, where it's one research center that they develop technologies that will benefit their core businesses, such as their aerospace business, their healthcare business, and things like that. So that was in summer 2017. I worked on composites for aerospace applications, and I just fell in love with the industry. I thought the materials were so cool. And while I was there, I was working in a small group of materials students. I was the only undergrad, and these three amazing people were all graduate students. So when we were talking in the office, they told me about grad school. In particular, Colin here was a student at UCSB at the time and still is. So he convinced me to look into UCSB to continue studying these types of materials. He helped me with my application and we became great friends over that summer. So I made it to UCSB. So I visited in spring 2018. It was my second time in California, my first time visiting Santa Barbara, and I just fell in love with the whole California vibe compared to the East Coast. We drank wine. I love wine. And I felt like I could still have a really good work-life balance in such a beautiful place. I can go hiking and go to the beach and things like that. A little bit more lessons learned and advice. I chose to join the ZOC group. We call ourselves Team ZOC. We are a really close, tight-knit group, and we made t-shirts. So this is Frank. The first piece of advice that I have is to just talk to as many people as possible. Like I wouldn't be here without just at the research center. I asked my mentors and my boss gave me homework to go knock on people's doors in the hallway and ask them, what they do and their career path. So I realized that a lot of people at that research center had PhDs. And if I wanted a job similar to that, I would have to get a PhD. So that's kind of my path, like means to an end kind of thing. And I still stay in touch with them and see them at conferences. So I think that's really beneficial. And in general, networking is just so important, especially in a field like material science, where as you're seeing over the past few weeks, there's so much you could do. So I'm studying aerospace materials now, but that doesn't mean I have to stay in aerospace materials in the future. In terms of choosing my advisor, I really, even though I fell in love with the aerospace materials, I think choosing your advisor over the research project is really important. I liked Frank because he was very application focused and he was able to talk about the big picture as well as the small details. And he had industry funding, which attracted me because I know I'm motivated towards application-based research. He's also a very good presenter and writer, so I knew he could also teach me how to communicate well, both in oral and written formats. And then overall, just be thankful for every experience and enjoy it. I didn't know I was going to be funded by a Japanese company, and I was able to go to Japan after in the summer of my first year. And so this is us visiting the IHI facilities, and it was just an incredible experience. Finally, I'll be realistic, grad school is very hard. So it helps to be friends with people in your research group or just build support systems so that when you're stressed, you can lean on people. So I find that really helpful in my group where we have a lot of fun through the good and the stressful times. Okay, so that's a little bit about me. I'm happy to answer questions about that, about my path at the end. But now I want to teach you and talk to you a little bit about turbine engines. And so here's a fun GIF of 100,000 flights that occur per day. And I hope you're as excited as I am to get back on a plane again and travel to other countries on an airplane. And what we'll really talk about is this amazing machine called the turbine engine. And I first want to talk about how it works because material science often focuses, especially on these applications, on very small parts within a larger system. So I usually talk to my family and people about what I do, and I start with the turbine engine. So let's take a look at the inside of a turbine engine. Here's a person for reference. And we're going to break down how it works just because I think it's really interesting. And I focus on materials towards the back of the engine here. So you can see there's lots of components that are very complex inside this engine. So if we take this and kind of expand it so we can talk about each part of the turbine engine, the first is the main fan, and the fan blades suck in air from the environment. The air can bypass the core, which consists of the rest of these components, or it can go through the core. The air coming through the main fan provides most of the thrust that's needed to get you up in the air. The air that gets through the core first goes through the compressors, and it's squeezed as it passes through the low pressure compressor and into the high pressure compressor. Then it enters the combustor where the compressed air is combined with jet fuel and you get a combustion process. And finally, hot exhaust gases blow out the back of the engine. And the hot gases causes these turbines to spin. Everything is connected to one axis. So as these turbines spin, it allows the front main fan to spin and suck in more air, and the whole process repeats itself. So the materials problem that I focus on is the high temperature materials in the turbine section of the engine. So in terms of material science, I focus on three main considerations for material choice in these turbine engines: thermal, mechanical, and chemical configuration environments. So let's start with thermal. We can go back to basic chemistry and talk about bonding. Each type of material has different types of bonding that holds it together. Ceramics often have the strongest bonds, covalent or ionic bonds, where ionic bonding is most popular in ceramic materials. Think about sodium chloride. Metals have metallic bonds, which are the second strongest, and polymer chains are connected with these weaker van der Waals bonds. So in terms of temperature capability, the materials with weaker bonds often have a lower operating temperature or melting temperature, and materials with stronger bonds have higher melting temperature. So ideally, we would like to have the highest temperature materials like ceramics in an engine. Other aspects of the materials that are important to understand is the microstructure, where you can have materials that are single crystal, such as diamond. These are really expensive and difficult to grow as one crystal, but they often have high temperature capability and really good properties. More common in ceramics and metals are polycrystalline materials, where you have a microstructure that looks something like this, where these things here are individual grains, and the size of these grains and the shape of these grains and the density, like whether they're completely compact or whether there's pores, all play a role in the thermal and mechanical properties of your material. So if we think back to our turbine engine, the coolest parts of the engine are the fan. So sometimes polymers are used in the composite materials on the fan blades. And the hottest is after the combustion process where the hot gases flow out. So we want metals and ceramics in the combustor and the turbines in the back of the engine. So in terms of thermal behavior, the goal here is to increase the gas temperatures that we use in the engine, and that in turn increases the engine operating efficiency. But over time, in the past 60 years or so, we've been really limited by the material melting temperatures themselves. So I want to talk through some things that we have done as material scientists to process and create materials to try to increase operating temperatures. And the first was done in metals. Common metals that are used in engines are nickel superalloys. And so we've tuned the microstructure from these type of grains to directionally solidified grains, where you have elongated grains, to single crystal materials that increase the engine operating temperatures. We have engineered some ceramic coatings that go on top of the metals that have a low thermal conductivity, so that the hot gases interact with the ceramic with high melting temperature and don't reach really the bottom of the metal that has a slightly lower melting temperature. Some really incredible feats of engineering are cooling channels that have been placed in these metal materials, as well as coatings that go on top. So these tiny holes are machined into these turbine blades, where air, instead of going into the combustion process, is redirected into these materials to cool them down. And that unfortunately doesn't help with efficiency, but it is kind of incredible when you think about how these things are made. And finally, what I'll talk about today is moving from metal materials to ceramics. And so this picture here is a picture of a turbine shroud. It lines the outside of the turbines, and it's made of ceramic materials. These are ceramic composites, and the white on the top is a coating. Now, ceramics, we have to think about, as well as metals, is the mechanical response in an engine. So these things are rotating, there's gases flowing, we're going up in the air and down again, so pressure is changing. So we really need to test these materials. And so what we do is test simplified specimen geometries in a tensile test. This is just an example of a machine that you may see in mechanical testing labs, where we grip the specimen on both ends and we pull it. So what we get is a force displacement curve, where we measure with this load cell the force on the specimen, and with this moving crosshead, the displacement of how far we're stretching it. So if we're thinking about high temperature materials of ceramics and metals, ceramics are generally strong, so you can pull them to high forces, but they're brittle, meaning you can't pull them very far before they break. And metals are ductile, so they don't have as high strength as ceramics, but you can really stretch them and bend them and form them before they break. So here are some pictures of specimens where a ceramic with brittle behavior would have a very flat, sudden failure, and have this sort of neck form before it breaks. And that's another reason why metals can be bent and shaped into all different types of shapes, where it's a little bit more difficult to form ceramics. And the last consideration is chemical. So like I mentioned, the hottest sections are in the combustor and the turbines. During the combustion process, the fuel is mixed with air to form some exhaust gases. So these exhaust gases can be carbon dioxide, water vapor, nitrogen, and oxygen. And what I'm particularly interested in is how these new turbine materials degrade in very hot steam environments. So the testing that we do in the lab is a little bit different. Sometimes NASA or these companies that create the engine parts have test engines that you can place your materials in and actually go through the combustion process. But on a lab scale, we have to make do with a simplified testing. So what I do is I use a tube furnace where I put my material in a ceramic tube on a plate, and I introduce air or water vapor into my materials, and I can control temperature with these heating coils. And then I use a microscope to look at the changes of the microstructure before and after exposure. You can also combine the environmental exposure with mechanical testing. So this is a sample that you can pull in a tension test and also introduce the water vapor and steam into a furnace that wraps around the sample. So really fun experiments, I think. Maybe I'm biased, but you're really trying to break this thing and really try to see what's going on. So we talked about a lot of aspects of these turbine engines and the research that goes on. And I just wanted to quickly plug the structural materials department because UCSB is really the academic center of turbine materials research in the country, possibly in the world. So I just wanted to plug a little bit more of the research that goes on that I won't get to talk about, but if you're really interested, you can head to the materials website and check out some of the faculty. They have lots of things on their websites. So I mentioned these coatings. A lot of research goes into fabricating coatings to protect these metals and ceramic materials. A lot of mechanical testing is done on the macro scale when you're breaking samples in a tension test, but also at a very small scale that another speaker later on will talk about in these things called dislocations. Microstructure evolution. So when materials are heat treated, the microstructure may change, and so people study that. We have amazing characterization facilities that we all share in terms of microscopes and other things. I'm going to talk a little bit about oxidation and environmental degradation. So there's a lot of research not only in exposing materials to water vapor, but when you fly over a volcano or a desert, hot sands, dust, volcanic ash gets sucked into the engines and degrade your materials. So that's a whole nother field of research. Additive manufacturing has been really big, especially in metals, in reducing the amount of parts that you need to put together. Composites, which is what we'll talk about today, not only testing them, but creating them, fabrication. Computational modeling is really important, and often we have coupled projects where we have an experimentalist that works with the modeling person. So that is true for my work as well. And finally, high temperature alloys. We're not going to completely move towards ceramics, where there's still a lot of research in creating new alloys that have higher temperature capability than the current systems right now. Okay, so let's jump into a little bit about my research and the ceramic composites. So Pat mentioned last week a little bit about composites in the polymer space. Now I want to talk about composites in ceramics. And in this case, we're combining two or more dissimilar materials for enhanced properties. And what we want is the high temperature capability that ceramics provide, but we really need strength and ductility, which individual ceramics do not give us. So this is a picture of a ceramic composite. Often they're called ceramic matrix composites because it's a ceramic in a ceramic. You can also have metals and ceramics that are in one composite, but in this case, all ceramic for high temperature capability. We have fibers here, these circular things, in two different directions. Sometimes they're in three directions just to give strength to the material. Just zoom in and break down the constituents that make up this composite. First is the silicon carbide fiber. These fibers are very high strength, and they govern the entire composite strength. So that's what gives it strength here. The second is a boron nitride coating that surrounds the fibers. It's designed to be a weak interface so that when cracks come in, it deflects around the fibers rather than cracking straight through the fibers, keeps them intact, and it enables the ductility of the composite. And finally, our silicon carbide matrix provides structure, protects fibers and coatings from the environment, which we'll talk about soon. Okay, so in terms of the mechanical behavior, which is what we introduced before in our force displacement curves, we can also create stress and strain curves. What we get before, as a reminder for monolithic ceramics, is very brittle failure. So this linear regime, and then we break at very low displacements or strains. But these composites are so interesting because you can see the ductility that they have compared to regular ceramics. So what happens is cracks are introduced into the matrix, and these cracks deflect around those really important coatings, and it keeps the fibers intact. So that allows us to increase our forces and stresses. What the fibers do is the fibers start to break and they can slide out of the matrix. And then when it finally fails, you get this really cool fracture surface where you have fibers that have been pulled out of the matrix. And that's what you see here. So this kind of messy fracture surface is exactly what we want to see, rather than a very flat, brittle failure that normal ceramics have. So we can test these not only in those smaller components, but larger ones with lots more fibers. So this tough composite behavior you see with lots of fibers in this vertical direction, but also the horizontal direction where fibers are splaying everywhere. Again, this is the tough composite behavior that we want to see. This sample was tested in a tension test at 800 degrees C, just in the lab air. But when we expose these materials to water vapor environments to try to simulate the exhaust gas, we get some complex behavior. So some of these fibers show brittle failure, where we have very flat fracture surfaces, like you can see here. Some of them seem to be unaffected by the water vapor and have tough behavior. And this one was exposed to cyclic loading. So you pull and release the load, and it failed just under 4 hours. And these materials really need to survive tens of thousands of hours in an engine environment. So we need to figure out what's happening. And if you take a closer look at the microstructure in the SEM, you see new species start to form, particularly around those really important boron nitride coatings. So we want to figure out what is happening when water vapor is introduced. But this picture, like I mentioned, is a little bit too complex to understand what's going on because we get such different behavior just within the same sample. So what I do is I break down that multi-directional composite and I study very simplified geometries. So this is a mini composite that has just about 500 fibers in one direction. So I study the microstructural evolution of those when they're exposed to water vapor. And then I also study just the coatings on the fibers themselves and just the fibers. So I'm trying to break it down and understand the more fundamental mechanisms behind the formation of those new species and the timescales over which they form. And eventually, all of the information that I learned at this level, this length scale, will be used to inform the testing. This is an airfoil that's used in an engine. And designers can use the timescales that we learn about these oxidation processes to determine when they need to repair parts or when they should be replaced before they catastrophically fail. So in aerospace, there's no room for failure, because if a material fails in your engine, you're going down and people's lives are at stake. So really understanding these mechanisms are important in this industry specifically. So I want to thank you guys for listening. Just a quick summary: working hard, asking questions, and making friends got me to grad school and is continuing to help my work-life balance and mental health. We learned about jet engine operation and engine materials in thermal, chemical, and mechanical environments. And I told you a little bit about my PhD research in understanding the fundamental mechanism behind composite degradation in water vapor. So thank you guys so much for listening. My email is listed here. If you have questions, I'd be happy to take them now.
Thank you, Victoria, for a great talk. If anybody has questions, please put them in the Q&A section. It can be about grad school or anything else you might have heard today. So for starters, I would like to ask did you have this specific project in mind when you were going to grad school, or were you open to kind of working on a few different things and this is what you settled on?
Yeah, I didn't choose my project. So when I came here, I knew I wanted to study these types of composites for aerospace just because of my internship that I had at the GE Research Center. And I do see in the chat, Dr. Cup was one of my professors at Penn State. So thanks so much for calling in, Dr. Cup. She was influential in helping me get those internships. So thank you very much. And when I got to UCSB and I just started chatting with Frank, he does a lot of different types of research. So we do coding research, we do mechanical testing. And so he kind of had this project in mind, but gave me options. And again, I didn't really know what I was getting myself into. So I was like, okay, I'll study oxidation. I like chemistry. I knew it would be a little bit more chemistry focused than mechanical testing. So I kind of just dove in. And the more you learn, I think, about a project, like the more excited you get, I think, because there's so many more complex parts. So I fell in love with it once I started learning more about it.
Yeah, that's awesome. I think it's great that you kind of had, you kind of knew what you wanted to do, but you were open to a lot of different options there. So for you, you talked a lot about like also being first gen going into college. So what for you was the hardest transition going from undergrad to grad school?
That's a great question. I think the transition was really focusing more on research and a little bit less on classes. So you take a few classes in the first few years, but the focus really was getting caught up to speed on the research itself and learning how to conduct experiments and analyze data. So at the beginning, I felt like I was paying really close attention to classes, spending a lot of time on my homework and things like that, which is important to learn like the fundamentals, but it was hard to balance both. I didn't do too much. Like I did some research in undergrad, but the balance is a little bit more heavy towards research in grad school.
Yeah, certainly different kind of vibes. And for those of you who might be considering grad school, also important to note, for most STEM PhD programs, you actually get paid to do research. So it's kind of like a job for a lot
Yeah,
of
and
us.
being first gen, convincing my family that I was going to move to California. Like, we're an Italian family, we're really close, like nobody really moves away. So they were like, you want to leave us? Like, don't leave us. And I had to explain, like, I'm not leaving forever. Like, I love you guys, I just want to go try this out for 5 years. I think if anyone's thinking about moving away and a little nervous about leaving family, like, it's been such an incredible experience. I have grown so much, I feel like, as a person, meet so many different types of people outside of my circle at home, and it has been such an amazing experience. And yeah, I do want to make my way back to the East Coast afterwards, but you can never, like, 5 years studying in such a beautiful place like this, like, you can't get enough. Yeah.
Yeah, it is kind of a nice little portion break. So you don't, just for that 5-year period or whatever.
Yeah.
Okay. Well, if anybody else has questions, please feel free to put them in the Q&A, and I'm sure Victoria would be happy to answer them during our next talk, which we're going to switch gears now. And Elias is going to be talking about some of his research. We have a recorded talk that we're going to play for him. Elias, would you like to say anything before we start the recording?
Yeah, so I'll say one quick comment. I made a mistake at one point saying research. I meant outreach. So you'll catch it, but I meant outreach.
Okay, great, thanks. So here's the next talk. And again, feel free to put questions in the Q&A anytime, and the speakers can get to them.
Hello, my name is Elias Sebti, and I'll be giving the MSA Research Roundup talk this week. My talk today is going to be about how, in my research, I combine experimental techniques of characterization with theory to really understand lithium transport and conduction in some lithium-ion battery materials. So let's get started with a brief outline of how I'm going to structure this talk. First, I'm going to talk about how I got to UCSB, how I decided to study batteries, and why I went to graduate school. Then I'm also going to move into a research section where I talk about my specific research and how I work with different characterization techniques to create a really nice picture of how lithium conduction works in a series of lithium-ion battery materials. First, a little bit about my path. I grew up in the Bay Area and I went to undergraduate at UC Berkeley, from which I graduated in 2019 with a Bachelor's of Science in Material Science and Engineering. I was lucky enough to get to call this building home for a bit. Hearst Mining Building is one of the most beautiful buildings on campus, and the Material Science Department is really lucky to have one of the sort of architectural crown jewels of the UC system. I started my PhD right after finishing at Berkeley, and I just went in right after during that fall. I study batteries because I believe that climate change is the biggest challenge, whether we like it or not, for our generation. We have to pursue a transition to renewable energies, and we have to get rid of fossil fuels. Fossil fuels are great. They're cheap, mobile, energy dense, and there's a reason we've been using them for so long. But we've realized now how much CO2 is generated from our use of them, and we need to build batteries that can compete with the fossil fuels and ultimately displace them from the market by making them cheap, mobile, and also energy dense. In 2017, I got my first opportunity to do research on batteries in Dr. Vince Battaglia's lab at Lawrence Berkeley National Lab. I got the opportunity by really emailing a lot of people, sending out emails to all the faculty at UC Berkeley who were working on batteries, but also a lot of the individuals, the staff scientists working at Lawrence Berkeley National Lab. And ultimately, Vince was nice enough to take me into his group. I worked on making cathode films, and then I made those films into batteries that I could then test. I got a lot out of the experience, really my first-hand hands-on experience with batteries. I also got some pretty unbeatable views of the Bay Area, if I might say so myself. But more importantly, I really had a desire to keep doing battery research. I knew that there was so much still to learn, and I wanted to learn more. So in the next summer, I worked with Dr. Mike Toney at SLAC, which is the national lab associated with Stanford. And I got the opportunity basically by reaching out to him and getting funded through the Department of Energy Science Undergraduate Laboratory Internship Program. So we worked at a synchrotron, which a synchrotron is really just a really huge ring of accelerated electrons. And as they move through this ring and pass through bending magnets and undulator magnets, they generate really intense X-rays. And so these are some of the most intense sources of X-rays that exist on this planet. Traditional X-ray tube sources that you might find in a lab are under 10 to the 10th order levels of brilliance, whereas the synchrotrons are on the order of 10 to the 20th. So they're really way more intense, and they're really impressive characterization tools. So I worked on a project that was on anode-free lithium metal batteries, which are basically just batteries where all the lithium is coming from the cathode and then is plated and stripped from the copper current collector. I was making batteries in order to allow them to be characterized operando in a synchrotron, which means basically using that X-ray beam during the operation of the battery to understand what's happening on the inside. So I really got very interested in the power of advanced characterization methods through this opportunity. But I also realized that I only had really seen academic research up to this point. And so I was interested in an industrial perspective. So I went to the Subin group at Lawrence Berkeley National Lab that had a collaboration with the Robert Bosch Corporation. I found out about this opportunity through a mass email through the Cal Material Science Department. And I got to work on this project that was concerned with using sodium ion batteries to do desalination. So just as how sodium would be put into and pulled out from, which we call intercalation and deintercalation, from a sodium ion battery cathode, we can do the same with sodium that's in water. And on the other side, get chlorine to adsorb to the surface of a very high surface area carbon material. And in the process, we can pull sodium chloride out of the water. So I designed this desalination testing station and made basically conductivity and pH measurements of the water as we were operating the system to understand how different materials performed. I also got to move into trying to characterize the system operando while the actual desalination was happening at the synchrotron. And I got a really important lesson in research, and that's that often research doesn't work. So in this instance, unfortunately, the measurements didn't actually pan out and we weren't able to get any data, but it was a really still cool opportunity for me to continue down this path of characterization and understanding what's happening inside of a material. So I got that industrial academic perspective, and I could say that sort of the contrast between the two is that industrial research is really motivated by precise goals and targets to hit with performance of a certain material or a system, whereas academia is more interested in understanding what's happening within the materials and how to improve that over time. In that opportunity, I also got to spend time as a full-time researcher, and I really appreciated that opportunity because it got to give me insight into what graduate school would be like. I realized I wanted to keep going with my education. I wanted to keep learning, and I also didn't want to go into industry, start making money, and then have to go back to graduate school where I'd be making less money. So I decided to go and apply straight to graduate school. I knew I wanted to have a hands-on research advisor based on my previous experiences with especially Dr. Subin, and I knew that that was hand in hand with a newer research group. So I found Professor Rafael Clement's group at UCSB that also had an emphasis on characterization and electrochemistry. Their goal, and our goal now, is to elucidate structure-property relationships in electrochemical materials. I got to talking to her, and unfortunately in that instance, I knew that I would have to bring my own funding to be able to attend. I was admitted to another school, but UCSB was still very, very tantalizing for me. So I applied to the National Science Foundation Graduate Research Fellowship, and this is a 5-year fellowship program with 3 years of really full financial support for your endeavors. It is a program that requires just 2 components to the application: a personal statement and a research proposal. And that research proposal is a really great thing to work on with the mentors that you've had over time, because it's really crucial for you to sort of spend time understanding the current state of science, which is really where the mentors can really help you, and also design experiments to try to learn new things to advance a certain field. Now, you don't need a fellowship to go to graduate school, but it can really open a lot of doors for you. And in this instance, UCSB was one door that I would need a fellowship to open. Now, there's other fellowships that exist aside from the NSF-GRFP. There's the ND-SEG as well as the Hertz Fellowship. So if you're looking for fellowships, I really recommend looking at these sources. Ultimately, I got NSF and was able to attend UCSB, where I've been able to find a really nice work-life balance. We work a lot in the lab, but when we're not in the lab, we get to spend time outside doing really fun things like surfing, climbing, or going to the mountains to snowboard. So before we move into the research, I want to give you a few tips that I've sort of learned along the way. The first is don't be shy. Introduce yourself to new people and stay in contact with individuals that you've worked with from your past. Having that sort of network of relationships is really useful for down the line when you're starting to, work on your NSF proposals, need letters of recommendation. Keeping in contact with these individuals can really help you down that path. I would be nowhere without the relationships that I've made through the research programs that I've done, and I really recommend that you work on those relationships as well. In that same vein, I would say give more than you take. Somebody, help them, and do your best to do that, because over time people will reciprocate and people will help you. And I think that it's one of the most important things in such a collaborative domain like academia. And also participate in scientific research if you can. What I mean by scientific research is sort of volunteering to teach science, to do demonstrations of experiments with, underprivileged communities or with just younger students, because it really can only take that little moment to ignite a passion in somebody for science. And it's one of the methods that we can really push to have a more diverse and really impassioned scientific community. So before we move into the research, I just want to share one quote that I think really embodies why I like to do research too. And it's that new knowledge is the most valuable commodity on earth. The more truth we have to work with, the richer we become. So with that, let's move into the science. And I do research where I work on combining characterization experiments with theoretical tools to understand how lithium moves and is transported through structures in lithium-ion battery materials. So really, how does a lithium-ion battery work? That's a great question that you might ask here. So a lithium-ion battery consists of three components here. On the left, we've got our lithium cobalt oxide cathode. In the middle, we've got our liquid electrolyte, which consists of organic solvents with a conducting salt, in this case, LiPF6 mixed in, and a graphite anode. Our battery at the moment is fully charged, and that's because all of our lithium is in the graphite anode. Now, as we connect the terminals of our batteries, we can now start to allow electrons to move through the external circuit and lithium ions through the liquid electrolyte so that they can go into the lithium cobalt oxide where they'll be really happy. Now, in the process, our electrons move through the external circuit and do work, and that's what provides the current for our devices. In our fully discharged state, all of our lithium is back into our lithium cobalt oxide cathode. So this liquid electrolyte that I mentioned previously, unfortunately has some pretty severe limitations. So they're made up of these organic solvents like ethylene carbonate and dimethyl carbonate, as well as that conducting salt like lithium PF6. One of these limitations is that the voltage range of stability of the organic solvents, as well as their temperature stability, is pretty limited. And that's because they will tend to break down at higher voltages, or they'll sort of volatilize at higher temperatures. On the other side is the flammability concern. So if you ever see videos of, Tesla's on fire on the side of the highway, or the whole Samsung Note fiasco, that's because the organic solvents were catching fire. Next, as the organic solvents sort of break down, they can create these sort of insulating films on your electrodes, which increase the resistance and will lower the amount of capacity you're able to extract from your battery. And finally, from the conducting salt is its toxicity. The fluoride anions that it contains can, when mixed with water, when mixed with air, can start to create hydrogen fluoride, and that is a really, really dangerous chemical. So one thing that we can envision is moving away from these liquid electrolytes towards a solid. And our battery architecture in that would look like a cathode composite, which is composed of our active material and electronically conductive carbon additive, as well as a solid electrolyte. And it's this solid electrolyte that we're going to pay a lot of attention to today. So it also acts as a barrier between our lithium metal anode and our cathode. So on the solid electrolyte advantages side, we've got a huge energy density increase that becomes possible by allowing us to go to higher voltages and implement a lithium metal anode into our construction. And these things are really what we're shooting for. We want high energy density if we want to displace the fossil fuels out of this. Next is the non-flammable. So the solid electrolyte that we're dealing with here is non-flammable and will not catch fire. It's also stable, so it's not going to become volatile at higher temperatures, and therefore our battery doesn't have to worry about being at those higher temperatures. And finally, it's that battery stacks become possible. So in a liquid electrolyte, we have to individually package every cell because we don't want our liquid electrolyte leaking out. Here we have no liquid and therefore no leaks are possible, which means that we can start to layer batteries on top of one another and have more sort of like module level energy density. Now we need some certain properties from these solid electrolyte materials. The first of which is a high voltage stability, which means we want to be able to be, chemically stable against both our cathode side and our lithium metal anode side. And that's no easy task, and it's often chemistry dependent. The next side that we want is to have high ionic conductivity. We want it to be really easy for our lithium to move across our electrolyte because that means that we can get these high currents in our battery. The problem with that is that, it's much harder to move lithium through a solid than a liquid. So we want to look at these structures, these crystal structures that can help us move the lithium faster. And this is really the aspect that we're going to focus on for the remainder of the talk. So today we're going to be focusing on crystalline inorganic solid electrolytes. That means that we don't have these sort of carbon, oxygen atoms within our material, and we're really focusing on inorganic compounds. On the other side, there's a lot of polymer solid electrolyte work that's being done, and some really great work that's being done at UCSB that Pat Getty was showcasing just last week. So on the menu today, we're going to be looking at layered lithium yttrium chloride and its sort of stacking faults that affect its conductivity. But first, let's talk about crystal structure. Let's consider this layered cake to be a crystal structure. We can tell that it's made up of a few series of sort of repeating layers. First is our cake layer, then is our cream layer, then is our strawberry layer. And we can tell that that's sort of the individual repeat unit of our cake. That repeat unit we call a unit cell. This unit cell is made up of a layer of cake, a layer of cream, and a layer of strawberries. Then we can start adding layers and start creating a cake and create our full crystal structure. At the same time, though, if we make a mistake in a layer, if a layer is misaligned or we, accidentally switch the strawberry and cream layer, these are called stacking faults. Now we're going to focus on lithium yttrium chloride, and this compound is a layered crystal structure. So it's made up of a series of 4 layers where we alternate between lithium and yttrium layers with chlorine. So then we build up basically layer 1, 2, 3, 4, and then we repeat with layer 1 stacked directly on top. This material, its conduction processes improve when we make it via ball milling. So there's 2 synthesis techniques we're going to look at today. The first of which is furnace synthesis, which just means putting it in a really hot furnace. And the next one is ball mill synthesis, which means I put my powders into these little jars with little metal or ceramic beads on the inside, and I start spinning it really fast. And basically I can trigger chemical reaction by smashing my powder between these sort of rocks. But really today, I want to talk about how we use characterization tools and theory, and we piece these little puzzle pieces together to create this general picture of what's actually happening in a material. So the techniques that we're going to look at today include X-ray diffraction to look at the structure, nuclear magnetic resonance to look at, what kind of chemical environments or sort of chemical neighborhoods you can think of our lithium and yttriums are experiencing. We can also try to understand how fast is lithium moving through our structure with something called pulsed field gradient, NMR, which NMR stands for nuclear magnetic resonance. And finally, we can try to fully understand everything and run these simulation models using density functional theory, which is really just a theoretical approach to all of this to try to simulate and understand our different structure models. So first, we're going to start with X-ray diffraction. X-ray diffraction is looking at the average structure of our material, and I want to point to the differences in here. Focus on these sets of peaks in the furnace synthesis. We can tell that they're pretty sharp on our furnace side, but as soon as we go to our ball mill synthesis, they become really flat and broad, and that's a sign of stacking faults. So we can try to create a model for this stacking fault, and on the left here, we have no faulting, and that means that just 1, 2, 3, 4, and then 1 directly on top of that. While in a stacking fault, we go 1, 2, 3, 4, And then our layer 1 doesn't line up perfectly with the 1. And it's not a drastic difference. As you can see, our crystal structures look pretty much identical. The difference, though, is that when we start conducting through the structure, this different environment is going to cause a lot of differences here. So we can start to look to solid state NMR to understand kind of what's happening within. So NMR is a really element specific probe. And when we look at our structure, we can tell that the yttriums in without 1 are going to experience different local environments. They're just different sort of neighborhoods, chemical neighborhoods around it. And that should be reflected if we run an NMR experiment. And when we run an NMR experiment, we can see that we get different local environments. The problem is that it's really hard to interpret this. I can see 4 peaks on the left. I can see sort of 1 blob on the right, but I don't really know what that means. So this is where I need to turn to theory to model really what's going on in this material. So I go to modeling in my theory calculations, which density functional theory, or DFT, allows us to do. And we use DFT to model the NMR properties of structures with stacking faults. So when I look at here at this plot, in green, I have structures that give me no stacking faults. And I can see that my sort of peaks are really well reproduced here. I see 4 bins that when I look at my NMR spectrum, it sort of correlates to these 4 peaks. And that's when I have no stacking faults. And I can even emphasize this when I turn that plot to the left, and I can see that it really falls well within these little bins. When I have stacking faults, though, I can see that this sort of perfect little bin representation breaks down, and that's sort of corroborated by that sort of 1 broad peak that we observed. Now I sort of want to understand the conduction properties of this. So I can start to use density functional theory to model lithium ion conduction and transport pathways through my material. So what we see here on the left is that we just mostly have chains going up and down here. And this is how lithium would really be moving through my material. But as I introduce the stacking faults, I create these sort of loop features. And these loop features, really what they're doing is they're increasing the connectivity between different lithium sites. And in that process of increasing the connectivity, we can start to get much better conduction through our structure. Next, I move to characterization techniques that allow me to specifically look at conduction. And so I use this PFG NMR, or pulsed field gradient NMR, to track lithium conduction as a function of temperature. And in the process, I can access activation energies for these conduction processes, which you can think of as, how easy is it for me to conduct? So I can see that when I have a ball milled component, I'm getting activation energies around 0.27 electron volts or 0.22 electron volts. But when I use a furnace synthesis, I get activation energies that have higher values. And this suggests to us that the conduction within our material that has stacking faults is much easier than the one that doesn't have stacking faults when it's made by furnace synthesis. And so we've created this now full image that, lower activation energies are correlated with stacking faults in the material. So I can sort of piece together all these different little pieces of the puzzle. I saw from my X-ray diffraction that I had stacking faults. I used NMR to sort of confirm it by looking at the different synthesis techniques. And then I gained an understanding of what my NMR spectrum and conductive properties would be from density functional theory calculations. And finally, I confirmed that in my material with stacking faults, we get easier conduction. And all of this was done by putting together a lot of different characterization techniques to get a full picture of the material. So with that, I'd like to thank my collaborators, all the people at National University of Singapore, Dr. Piero Canepa and Henying Chen have been incredibly helpful in this. Dr. Hayden Evans has been instrumental in all of our diffraction data. And on the NMR side, I've got a lot of help from the Clement group. So I really want to thank everybody that's made this possible. Research is a collaborative effort, and advances don't happen unless a lot of people are working together. Next, I'd like to also thank the funding sources on the NSF side, the MRL, the Materials Research Laboratory at UCSB, for providing some fantastic characterization resources. And finally, the Material Science Association at UCSB that put on this webinar and allowed me to give this talk. And finally, I'd like to, sort of open it up to questions, but also encourage you, reach out. If you have any questions or just a general interest, reach out to me, send me an email, and I'm more than happy to field any sort of questions. But yeah, I'll open it up to questions now from the audience, and thank you so much for your attention today.
Awesome. Thanks, Elias, for that talk. Reminder, if you have any questions or comments, you can put them in the chat or in the Q&A section. So while we're waiting to see if anybody has any questions, I wanted to ask, so you spent, it seems like you had a lot of different research opportunities throughout undergrad and, obviously in grad school too. But did you pursue those because you knew you wanted to go to grad school? Was that always sort of the goal, or did doing that make you want to go to grad school?
Great question, Caroline. I think I started early as just kind of maybe research could be interesting in the early stages. And then I slowly realized that, it wasn't like other jobs. And basically every research experience I got, I was like, okay, no, this is cooler than I thought it was going to be. And over time, I just sort of basically settled on that. And by the time I think I was around a junior or senior, I was pretty set on going to grad school.
Okay, cool. So start early, figure out different things that you might like. Mm-hmm. We got a question in the Q&A. Do grad students usually do a lot of different types of experiments, or do they usually focus on one? I think you're probably well positioned to answer this because you presented a lot of different things today. Yeah,
no, that's a really good question. I think that it really depends often on your group. Some groups basically collaborate with other groups where sort of one group are experts in X-ray diffraction. The other group is going to be the experts in NMR, and then the other group is going to be the theory expert. I sort of knew that I wanted to get a blend of that experience, and so I knew that the Clermont group was a place where I could sort of get experience with a bunch of different techniques at once. But it really depends on the group and how focused the expertise of that group is.
Yeah, cool. So you picked your advisor partially because you knew you would get these experiences you wanted doing different experiments and things like that.
Precisely. Yeah.
Great. I had one other question. So when you talked a lot about how you got funded by all these different things throughout doing your research opportunities. How did you find out about all of these different funding things? Was it through your university, through separately just looking it up, or how would you suggest other people go about looking these things up?
Yeah. So on the funding and fellowship side of things, there's often opportunities through your university to give some sort of information, some sort of a seminar or something like that about funding sources. I only really found out about the fact that fellowships exist the summer before my senior year in college, and once I basically found out about one, I kind of was like, okay, well, there probably isn't only just one. And so at that point, it was spending time on the internet trying to find all these different different fellowship opportunities. But yeah.
Great. Well, we'll give it another minute and see if there's any more questions. But thank you to both of our speakers. Victoria and Elias gave nice talks today. And if anybody has any other questions for them, they can also reach out directly to both of our speakers. You have their contact information, or you can go through the channels you use to hear about this to ask for their contact information if you didn't have a chance to write that down. Cool. If there's not anything else, we'll go ahead and conclude here today. Thank you both. And we'll see you all next week for a couple more talks by Raj and Ashley. Thanks, everyone.
Bye, everyone.
Thank you.
Bye, everyone.
Bye-bye.